Today we're going to talk about field weakening and other arcane methods for increasing your motor speed. One of these arcane methods is space vector modulation versus sinusoidal commutation. And the whole idea for this is to take your motor voltages that you normally apply, like sinusoidal vectors to the current, kind of like a generator. When you turn a generator, it generates UVW voltages. With the problem with that is the voltage is constrained to the center, and you never get full voltage across a pair of wires. So when you're at a peak, say for you, V and W are equal and opposite minus. So that's traditional sinusoidal commutation and models just like a generator. With a space vector modulation, we're trying to get the full current to the hexagonal limit, and we do that by not constraining the center. And so pictorially, the back EMF voltage, or the commanding voltage, will no longer look like a perfect sinusoid. It has an irregular shape, but the advantage is that when your U is near peak, V and W are near peak. And here, actually, when U is peak, V is peak. So full voltage across a pair of wires by unconstraining the center voltage. It's allowed to float or drift around. And so that's basis of space vector modulation, and it gives us more of the available bus voltage. And that's in theory, of course. The other thing I want to mention is the field-oriented control, which is to optimize the torque in the motor. And so we've moved away from just plain old trapezoidal commutation into a field-oriented control, which has to do with the placement of the current vector. When you got Eli the Iceman, E leads I in an inductive circuit. So you push your voltage ahead of the current, thereby gaining a perfect 90-degree angle between the current vector and the magnetic vector on the motor. And this D and Q space vector modulation for real and imaginary vectors helps increase the torque of the motor, which oftentimes gives higher speed too, unless you're starved for voltage. So that's the other way to increase your speed, is just increase your voltage. So today we're going to look at a motor which is said to be a 48-volt motor and trying to approach 10,000 RPM. But in actual fact, the back EMF constant is 5.1 volts, plus there's some IR drop. So 48 divided by 5.1 gives me about 9,400 RPM if I had all 48 volts to the motor, which of course we know this is a PWM amplifier and there's some IR drop, so we're not quite hitting the speed. So let's see what we can do, maybe field weakening, maybe other methods for increasing our speed. So the first method I like to talk about is based on the speed you want to go and the number of poles on the motor. So when we multiply these numbers together, we tend to get so many cycles per rev, and that means the current vector needs to rotate at that rate. So what I've done here today to test the open loop speed is just enter all my data and set it to a current mode. So this is just a pure current mode test. And in a current mode test, I can command a certain amount of current. So on my program current, I can set 1 amp, and I have not tuned the current loop. These values are they're not even calculated values. They're worse than calculated, but just want to show the point of the matter that the current loop frequency is important when rotating a current vector. The bandwidth cycles per second must exceed the vector rotation, speed divided by, 90,000 RPM divided by 60 times the pole count. Anyways, I'm going to enable the drive, and we'll see here this is a XLNet Plus drive with all the fancy features, including field weakening, driving a Maxon brushless motor with high resolution DISC encoder, and it's spinning pretty fast. I got about 7,000 RPM, but my current loop bandwidths are too low. So if we increase our current loop bandwidth to more reasonable values, the speed of the motor increases. I now have 8,500 RPM, which is pretty good. And we talked a little bit about circular and voltage limiting. We'll see that in the field weakening. With the field-oriented control, we optimize the torque versus the back EMF phase advance. So if we do a phase advance, we may get less torque and more speed, but that's assuming we've run out of voltage. So you can see in the diagram for the field weakening, there's a circular limit. We can turn that circular limit off by undoing the space vector modulation. And then what we should get is a new voltage limit. And by moving the current vector phase advance, you'll see there's an increased speed area where the ellipse is no longer a circle for the back EMF. We squeeze the current vector, at phase advance the current vector, and it squeezes the back EMF. So lower back EMF means you need less volts to go faster, but at the same time, the back EMF, if you raise the back EMF, lower the back EMF, then the torque constant changes and you get less torque out of the motor. So you don't get anything for free, but normally the stator current is in an optimized position for forward or reverse control, and what we're doing is we're pushing it towards the position that it shouldn't be in for optimized in both directions. So that becomes a field weakener. And this is just a procedure that we're going to follow today about how to accomplish this. So back to the current loop bandwidth, which is important. We also have circular or hexagonal limit, smoothness versus a little bit of a bumpy ride. And we hear it there a little bit. It's a little bit noisier. But what you'll remember is the circular limit here limits the voltage. I'd like this voltage given back to me between the circle and the hexagon. This extra little voltage per electrical cycle allows me to go faster. So with this voltage, my speed has further increased to 9,000 RPM. To turn off the field-oriented, the space vector modulation, the bus clamping, so that constrains the center to zero, and that unconstrains it. So I'm not seeing much of a speed effect here. There may be a torque effect, of course, but the speed at this point we're voltage limited, so we're not gaining much speed out of it. The other effect that we're going to show is how to do the field weakening. And normally when we do the phasing of the motor, we go for an optimal phasing for the phase offset. So I have a black indicator, that's the phase, followed by the feedback, which is in red. And there's a little lag in both directions. That's normal with a little load or friction. But if I had like a wrong value in here, you'll notice that the black indicator is now in a wrong position for the feedback. So our phase is off by like 90 degrees. So I'm going to put that back to 170 and see what the optimal phasing for forward and reverse is. So this is normal optimal phasing without any field weakening, nothing funny going on there. But if we do apply the same principle, and I advance the phase angle, I can see that my motor does go faster. So my speeds can increase based on the fact that I advanced the phase, and that's going to be sort of the proof in the pudding that my phase advance increases speed in this direction. So I'm going to set it back to optimal value. And then instead of doing the phase advance manually, we're going to use a gain schedule. So after testing out the theory that you get an improved speed, you'll see here that the gain schedule is not active, and I can test it. If it becomes active, then I'll have to turn it off if I don't want to use it. So this new parameter 19F is the parameter that we're going to adjust based on use your actual velocity, adjust the phase, the absolute value of the parameter, and there's a table. I'll show you the table in a second. And we have to calculate the actual value of the counts in units of 0.1 counts per second. So what I did for this was to program a speed and velocity mode and then read the parameter, the OA6AAAB, that's hex. And then I got the value in units of 0.1 counts. So I just converted this from hex to decimal, and you see the decimal equivalent at that speed. So here's the 19F parameter, and it's scaled 32,000 is 180 degrees, so minus 32,000 is minus 180 degrees. So again, you can see the parameters I calculated for 8,000 RPM in units of 0.1 counts per second with 0 phase advance. And then as the speed increased, 9,000, 10,000, I'm gonna advance that phase angle. And so this is normalized to about 90 degrees. So you can see minus 90 is about 16,000. When we have the gain scheduling running, you'll see that the gain schedule is active, and then here's a little display of actually reaching 9,500 RPM. Even though I'm commanding 10,000, I'm a solid voltage limit. So phase advance field weakening gave me probably about 5% more speed, along with all the other factors too. So from like less than 8,000 to more than 9,000, so that's a significant increase. 10% altogether, but just the field weakening gave me a little bit too. And you can see here that if I get this 19F parameter, it changes over time. So to do the gain schedule, you go to gain schedule, you select commanded velocity or actual velocity. I like to use actual velocity, use the absolute value, phase adjust. Set up a table for three values. So at this speed, 8,000 RPM, I have 0 adjustment, and then 9,000, 10,000, and I go from 0 to 45 to 90. So 32K would be 180. We don't want to do 180 degrees because that's like flipping the vector all the way around. The motor goes the other way, so don't do that. So save to flash, and you can see in the control panel that the CVM control program is running, and then we get the benefit of the field weakening. See 19F. Get 19F, and you can see at this speed the phase advance is approximately 45 degrees. So thanks for watching field weakening and other arcane methods for increasing your motor speed. Talk to you later.